Hi everyone. Today we'll be taking a look at Unit 2.2, and I've kind of combined two shorter sections together, and we'll be taking a look at shortcuts for proving triangles similar to one another. So we know that if two polygons are similar, that means that all of the corresponding pairs of angles are congruent, and each pair of corresponding sides are in proportion. But that's a lot of information to prove, so we'll take a look at the minimum amount of information needed in order to make a conclusion about a pair of triangles being similar or not similar. So the first shortcut you can look for is called the angle-angle similarity. It says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So if you take a look in the first triangle, we have angle B that measures 80 degrees, and in the second triangle, angle D measures 80 degrees, so we have one pair of angles congruent. And then we have angle C congruent to angle E because they both measure 24 degrees. So we can write a similarity statement and say that triangle ABC is indeed similar to triangle GDE. Remember, when you name triangles similar to each other or polygons similar to each other, their corresponding parts, the corresponding sides have to be proportional, but corresponding angles have to be congruent. So make sure you name them so that the congruent angles are lined up. So these two triangles are similar by the angle-angle similarity postulate. Okay, in our second shortcut, we'll take a look at the side-angle-side similarity shortcut. And it says if an angle of one triangle is congruent to an angle of another triangle, and the sides including those angles are in proportion, then the triangles are similar. So definitely see that angle B in the first triangle is congruent to angle T, and now it's time to take a look at the sides. So in the first triangle, we have a side length of 6. That's the shorter of the two given sides. And so that's going to correspond to the side length of 3 in the second triangle. And what we need to prove is that that ratio is equal to the ratio of the other two corresponding sides, 8 to 4. And you can see pretty quickly that both of those reduce to 2 over 1, or just 2. So those corresponding sides are proportional, and the included angles are congruent. So therefore, we can say that triangle ABC triangle ABC is similar to triangle STU. And again, just pay attention to how you name it. Notice that I went along the side length AB first in the first triangle, and that was the shorter of my two legs. And so I want to go along line segment ST in the second triangle. And these two are similar by the side-angle-side similarity postulate or theorem. All right, our third and final shortcut is the side-side-side similarity theorem. It says if the sides of two triangles are in proportion, then the triangles are similar. So you want to compare the sides of the first triangle, which have lengths of 3 and 4 and 5. We're going to compare these to the side lengths of the second triangle, and we want to do this in order. So shortest side in the first triangle gets compared to the shortest side in the second triangle. Medium length of the first triangle, which is 4, gets compared to the medium length in the second triangle, 12. And finally, the longest side of the first triangle gets compared to the longest side of the second triangle. And notice that all three of these fractions reduce to the same thing, 1 over 3. So therefore, our two triangles are similar by side-side-side similarity. Okay, again, just take note of how you name the first triangle. If I name it triangle ABC, I'm going short side to the medium length side to the longest side. You have to follow suit with the second triangle and call it triangle MNP. And again, they're similar by the side-side-side similarity theorem. Okay, now we're ready to test this out and give a give a try to a few problems in determining if the triangles are similar. So it says write a similarity statement and list the method used. Remember, when we write a similarity statement, we're going to name the two triangles. Okay. So in the first set, in part A, we have an angle of 50 degrees and a 90-degree angle, and that forces this third angle to be 40 degrees. Remember, the three angles in a triangle add up to 180, so 50 plus 40 is 90. 90 plus 90 is 180. Okay, what's great about that is we can now see that we've got a pair of angles congruent down here, and the right angles, of course, are congruent. So yes, these two triangles are similar by the angle similarity, and now we have to name them. If I name the first triangle GHI, similar to, and I have to name the second triangle JLK. Use those angle measures to help you get the names in the right order. Okay. In part B, it certainly looks like we're going for side angle side. We have angles congruent, 85 degrees and 85 degrees. Now let's compare the sides. 9 is going to be compared to the shorter side in the second triangle, so 9 over 6. We want to see if that's equal to 12 over 8. We know that 9 over 6 can be reduced by dividing both the numerator and denominator by 3, so that gives me 3 over 2. 12 over 8, you can divide both by 4. That also gives me 3 over 2. So these two triangles are similar by the side angle side similarity, and I can name them triangle EFG, and it's going to be similar to triangle AJR. In our final pair, it looks like we're going for the side similarity, so let's set up three ratios. We want to prove that all three pairs of corresponding sides are proportional. So from the smaller triangle, I have side lengths 5, 12, and 13. So 5 would correspond to 10, 12 would correspond to 24. I fixed that. And 13 would correspond to 26. And it's really easy to see that all three of these fractions reduce to 1/2. So they are similar according to the side similarity. And I can call the two triangles KJI, similar to triangle NPM. Okay, so KJI went along the medium length side first, and starting from where the longest side and the medium length side meet. So I want to start at point N in the second triangle and go along the medium length side there too. Alright, and exercise 2, it says use the diagram to complete each statement. Notice that we have parallel lines in this picture, so the top line and the bottom line are parallel, and they're cut by this transversal here, and that's going to give us alternate interior angles that are congruent on this side. They also have another pair of alternate interior angles that would be congruent. Angle B would be congruent to angle D. Right there, that's enough information to say that the two triangles are similar by the angle similarity. You could also choose to work with the vertical angles in here because, of course, vertical angles are congruent. So triangle ABC is going to be similar to triangle EDC. Okay, then you see what I did there. Angle A corresponds to angle E. Those two are congruent. Angle B corresponds to angle D. And finally, the vertical angles will correspond to each other. Just going to jump down to part C right below here. Angle B is congruent to angle D. Okay, jump back up to part B. This can give us a ratio of the three pairs of sides. So AB corresponds to ED. In the same way that BC corresponds to DC, and the same way that AC corresponds to EC. Now, what that allows you to do is plug in numbers. For example, AC right here is 4, and that corresponds to EC, and EC has a length equal to 6 in that second triangle. All right, over here we have 12 in the denominator. Notice that that is line segment DE. and that compares to line segment BA. So we're going to have an X in the numerator. This is actually going to help us answer part E, where we have to solve for X. So I'm going to do the work for solving this proportion down here. So cross multiply, take 6 times X, so you get 6X. Take 4 times 12, and that's going to give us 48 on the right-hand side. So 6X equals 48, and then take and divide by 6. So X is equal to 8. Okay, solving for Y. Well, notice up here that we had this ratio where we had two numbers in there, 4 and 6. If we reduce that, that gives us our scale factor. And we need that fraction because it has two numbers in it to help us solve for Y. So Y is the segment over here with line segment DC. So we want to use the other ratio, BC over DC. So from the diagram, BC is equal to 6, and DC is labeled with Y. Cross multiply, we get 4Y is equal to 36, because 6 times 6 is 36. Take and divide both sides by 4, and that gives us Y is equal to 9. And that's it. So similar triangles can be used to solve a lot of real-world application problems, and one of the most common, or actually the easiest things to do, is to use the shadows formed by the sun and an object. And by measuring the shadows and comparing them to the length of your shadow, you can actually calculate the height of something that otherwise would be really tricky to figure out the height of. So it says in number 3, Kim wants to find the height of a certain tree for a report for a biology class. Her method uses shadows as shown in the diagram below. She measured the shadow of the tree and found it was 5 meters long. So she took a tape measure along the ground and measured it to be 5 meters. She measured her shadow and found it was 0.8 meters long. So notice how she stood there, like she lined up herself with the tree so that their shadows met at the very tip, okay, right here at angle S. Now, I just put those marks in there because hopefully you see that there's a smaller triangle and a larger triangle, that they overlap, and they're similar to one another by the angle-angle similarity. Each triangle has a right angle, and then again they share angle S in common. So the similar triangles could be called triangle SCH, and that's going to be similar to triangle STR. Okay, it says in part B, complete the proportion. Well, line segment SC, which is Kim's shadow, would correspond to line segment ST in the big triangle, and line segment CH, Kim, and her height, would correspond to TR in the big triangle. In other words, Kim's height corresponds to the tree's height in the same proportion or same ratio as her shadow corresponds to the tree's shadow. So now we have to plug in some numbers. It says if Kim is 1.6 meters tall, how tall is the tree? So I'm just going to put an X in there for the height of the tree. So we want to compare, actually just fill in the blanks here, compare her shadow, 0.8, to the tree's shadow, 5, and set that equal to her height, 1.6, compared to the tree's height. So you can take 0.8 times x and write it as 0.8x, take 1.6 times 5, and that actually gives us 8, and then take and divide both sides by 0.8. That's going to give us x is equal to 10, and it's in meters, so the tree is 10 meters tall, or about 30 feet tall.